to the tutorial over vectors, you should be writing for page 19. That's the notes that we're working on. Page 19. Scalar and vector quantities. We're going to compare the two right now, and it's important that we understand the difference. A scalar is a quantity that is going to fully describe the magnitude. An example of this is going to be our time, our distance, and our temperature. Vectors are quantities that are fully described by both the magnitude and the direction. So an example of that is velocity, force, and displacement. And make sure that you're understanding what the word magnitude means. It is an amount or a size of something. So with vectors, the difference between the two of a vector and a scalar is that we're really looking for the direction. And so we're going to be learning a new way of how to find directions of things using trig. So it just keeps getting more fun as we go along. So how do we represent a vector? A vector is represented by a line that we call a tail, and the head of it is an arrow. So the line represents the magnitude in length, and the arrow is going to represent where the object has stopped at that particular journey or part of the journey. So the arrowhead is going to show the direction in which the object is going. So now we need to talk about the difference between distance and displacement. And you may feel like that these two are pretty much the same, but they're not. They're different. And in physics, we're going to talk about why they're different. So distance is actually a scalar quantity because it's going to refer to how much ground that an object has covered in its journey. So it's going to be the total path or how far that the object went. Displacement, on the other hand, is a vector quantity. So remember, vector tells us a particular distance. So we have a magnitude, but we also have a direction. And that direction is in reference to how far out of place that object is from where it actually started. So it's a change in position from an original location of the object. So here we have a little cross-country runner, and she has traveled a distance. And her distance traveled is from A to B, then B to C. So her A to B is actually 300. Now you can write this a couple of different ways. You can actually write it how it's drawn, which is 200 meters plus 100 meters. And then she goes from B to C another 100 meters. You can also write this 300 meters plus 100 meters. It just depends on how you look at it as an individual. It doesn't matter to me which way because the total meters that she went is going to count up to 400. So there's that rule again of it does not matter how you add them. Well, we haven't talked about that rule just yet, but it doesn't really matter how you add all the different vectors, just as long as they all add up to the same number. So 200 plus 100 plus 100 equals 400, and 300 plus 100 equals 400. So that is the total distance that is ran. But what is the displacement? Notice that she starts out at A and ends up at C. So this is where she stopped. So she ran 300 meters all the way to B, and then she ran back towards where she started for 100 meters and stopped, which means that she was 200 meters away from her original position, so we would subtract out that 200 meters. And so that then gives us a displacement of 200 meters. And so that is her displacement. So now we're going to look at the difference between speed and velocity. Speed is a scalar quantity that's going to refer to how fast an object is moving, and we are going to be able to find that by using the formula a total distance divided by time. So if we wanted to find the runner's distance, or excuse me, speed, we would have taken her total distance, which was what, 400 meters, and divide that by the time if we had timed her or if we had been given that information. Velocity, on the other hand, is different. So you may have been taught in 8th grade that velocity and speed are the same thing. The only difference is the direction, but you end up with the exact same number. Well, here in physics, it's not the same thing, and we don't end up with the exact same number. Velocity is a vector quantity that refers to the rate at which an object changes its position. So velocity is going to include the direction. So we're harping on this word direction. So velocity then is the displacement divided by time. Now remember, displacement is, its definition includes a change in position of the object because the object is no longer in the original place in which it started. So displacement in and of itself, that is actually a change in direction. Okay? So, having said that, let's talk about Tom. Tom likes to go on a walk, and Tom likes to walk this way. He likes to go 4 meters east, okay, and then he'll go 2 meters south. Now, when we're drawing our vectors, keep in mind that you don't have to, like, well, obviously on your sheet of paper you can't measure out 4 meters because your paper's not long enough. So give yourself a scale that's going to fit to your paper. So here my blue line is, that represents 4 meters. So my 2 meters should look like half of my blue line. Actually, I kind of jipped it a little bit, but it'll be okay. And then he goes west for another 4 meters. And then he goes north for another 2 meters. Okay? So, what is Tom's total distance? Tom's total distance can be added up by taking all of those numbers, 4 meters plus 2 meters plus 4 meters plus 2 meters, and that gives us a total of 12 meters. I want to know what Tom's displacement is. Tom's displacement is 0 because he ended up in the same place that he started. So 0 meters. Now we want to average, or we want to get Tom's average speed. Now remember, we take the speed by taking the total distance of the object traveled, dividing it by its time. Our total distance was 12 meters for Tom, divided by the 2 minutes that it took him, which gives us 6 meters per minute. I'll put the N there. What is Tom's average velocity? Tom's velocity, remember, is displacement over time. His displacement is 0. His time is 2 minutes. So it doesn't matter what's on the bottom. His displacement and velocity is 0. Well, if you remember, velocity means direction. Well, change in direction. And his direction didn't change. He ended up in the same place that he started in, so that's why his velocity is 0. So, moving on. We're going to talk about how we add vectors. And so we look at vectors a couple of different ways. When we add vectors, we can line them up head to head or head to tail. Okay, you can see we've got vector A and vector B, and we just will add them together, and that'll give me what we could call C. But which is our resultant, okay? Or we can look at it a different way where we have vector A and vector B, and vector A and B, we've got to find the resultant, which actually gives us this triangle C. So we have a resultant C. If we want to know the resultant of A and B, we're going to have to find C. Now obviously we're going to use trig to find that. Well, it's important to introduce right here that our resultant vector is the result that we get when we add up all of our vectors, and it is drawn from the starting position to its final position. So if you look at C, we started at the end of A's arrow or A's tail, and it draws all the way to the head of B. So that's the resultant vector. The resultant vector for the triangle over here is basically the hypotenuse, C. So when a vector is at an angle, and we have a vector here that's at an angle, C is at an angle, the sides are called the x component and the y component. And so now we're going to kind of bring back something that we already know. We know that the x component or the x-axis is always horizontal and the y-axis is always vertical. So there's our x component and our y component. And so we can look at this and we can say that our angle is to the x component or the horizontal. Well, what's our angle? Well, our angle is always where the starting point is, right there. Okay, that's where our angle always is. That's our starting point. That's where we started. That's how we identify our angle. So our angle is horizontal, or we have an angle to the horizontal. We could say it that way. Our angle is to the horizontal because we're going to have some problems like that. Okay, so I want you to, for a moment, watch these until you can see all three of these little cartoons moving. So you can pause to see that or watch that. Well, no, you can't pause. So I'll kind of give you the time. I'm sorry, because if you pause the video, you won't see these things moving. But what you should notice here is we start with A and started with D here, and over here we started with C. And we drew our vectors differently. So when we did Captain Pythagoras lab, everybody had a little treasure box from which they pulled out their instructions. So your group may have started with 5 paces, while another group across the room may have started with 10 paces. But ultimately, everybody ended up pretty much in the same spot. The one on the far left is a little bit out of range, but the point that we're trying to make here is that it does not matter how you or what order in which you add all your vectors, your resultant or your total traveled is always going to be the same. It will always be the same. Okay, and so we have a displacement here that you can see with that little green arrow, and we're going to be adding to that here. So we're going to start talking about how we can find the location in this particular situation, which we did not do with Captain Pythagoras. So we're building on what we've already done before we even introduce vectors. So how are we going to tell direction? We're going to tell direction by talking about angles. So angles from 0 degrees to 360. And if you look at that compass, and this is probably, not probably, this is what you're going to need to write down. We have north, which is represents the 90 degrees angle. West represents the 180 degrees. South represents 270 degrees, while E represents two angles, 0 degrees and 360 degrees, depending whether you're above east or below east, okay? So let's, our orientation is north is always up top, okay, and west is going to be on the left. If you look down at the bottom, you just see this little tick going, showing us the different degrees, okay? Notice this little tick is actually representing a vector, or a hypotenuse, actually. And so in the next few slides, we're going to be introducing how to find the location of an object. So I want you to look over here to the right side of the screen, and we have these red arrows. These red arrows are representing hypotenuses, or they're representing resultants, okay? We don't have our y and our x component on here, but we can actually draw our y and x components if we want to, because we just introduced an x and a y component. So I will draw my x and y component where I start. So where's the starting of an object's movement on what we call a vector? At the beginning of the tail. So this right here is my starting point, right here. And so I can draw a compass right there. Now the reason why I want to draw that compass is because it's going to give me my x and my y, okay? Now if my hypotenuse or my vector or my resultant is even with my x component, my angle is a 0, okay? All right, so let's go to this next one. Here I've drawn it off. Let me fix it. Okay, so there's my compass. My compass is telling me here then that I have an angle that's 27 degrees to my x, or horizontal. So this represents my horizontal. So this right here would represent my y component. Okay, over here, here's my x component, here's my y component. So this right here continues on with my x component. My x component continued that way. Okay. Over here, here is my starting place. Okay, here is my my hypotenuse. My angle would be right here. Right here's my angle. Over here, here's my starting place. Remember, we always start in the beginning of where the object's movement is. And here is my hypotenuse right here in the red. So this is my x component, this is my y component. All right, so here are how we identified x and y component. And I've showed you that we need to draw our angles, or excuse me, draw our compasses at the very start. So there's a couple of more things that I want you to add, and I can't reach my compass, so I'm going to have to draw this over here. So inside of the compass that you drew on your paper, we are going to label our quadrants. And in our quadrant from 0 degrees to 90 degrees, there's some information that you need to know. If your angle, okay, if your angle is moving away from your 0 like this, away from 0 degrees, you are going to add your angle to 0, okay? So if you look at this one right here, where it says 27 degrees, and you notice where the compass is, there's 0. I'm going to away from 0 degrees. I am going to add 27 to my angle, 0 to my angle, and my angle is 27 degrees. So here's a rule, 0 plus theta if you're going away from. If you're moving this way, okay, if you are going this way, if your angle is going that way, or if you're going towards the 0, depending on where your x and your y's are and your hypotenuse is, you're going to take your 90 degrees and subtract it out of, or subtract your angle out of the 90 degrees. This will make more sense as we move a little bit further in the notes. Right now it's a little bit confusing. Okay, so just trust me. In this next quadrant, okay, it's going to be 90 degrees plus the angle, or 180 degrees if your angle is going away, okay? if your angle is going away. And it's all relative to where your angle is and where your hypotenuse is. It'll make more sense later. Just get these instructions down. And then in the third quadrant, you are going to add to 180 degrees, okay? Or you're going to subtract your angle from 270 degrees. And then in the last quadrant, you're either going to add to 270 degrees, your angle, or you're going to subtract from 360 degrees. Okay? So you might want to write down what I said. If you are going away from the angle and what away from the if you're going away from 0, that is always add. But if you're going towards the 0, that is always subtract. Okay? All right, just make sure that you know those. And when we get into the problems, it'll make more sense. Okay. So let's do this example. Now, this example is the resultant velocity of the picture. Okay, so we want to know what the resultant velocity of the picture below is. Now, velocity is telling us we want to know the direction. We're going to get the resultant velocity. My little canoe person is going across the river. The river is creating a force or resistance against this. So it's going to cause the velocity to change. So in order to get my velocity, not only do I need to find out where all that good stuff is, I also need to make sure that well, the resultant, which would be the hypotenuse, I also am going to have to find the exact location of my canoe. So this problem could get pretty complicated. So let's draw it over here. I know that the canoe is going this way, and that's where the fella's trying to go, this way, okay? So this is my starting position right here. The wind, though, the wind is doing this. So we are trying to find this, okay? And I know that my arrows are meeting right here. It's because I have two forces working against one another. But this is my starting point, and because this is my starting point, I also can draw my compass right here. I'm going to go ahead and draw my compass right there. So when I draw my compass right there, my angle of interest is right here, okay? This is my x component, which is at 0 degrees. This is my y component. My y is 3 kilometers per hour. My x component is 4 kilometers per hour. So I can find C, my hypotenuse. So let's give ourselves some steps. The first thing that we need to do, I'm going to write it over here in the black, is we need to draw a picture. Okay? Draw a picture. The second thing that we have to do is we got to do the Pythagorean theorem because we want to find our resultant. So that's going to be our hypotenuse. So let's take care of that. So c squared equals 4 kilometers per hour squared plus 3 kilometers per hour squared. I got to get rid of this square on the c. So I'm going to put this in the calculator. So I'm being lazy. I'm not writing the unit right now just for time's sake, okay? So if you put that in your calculator, you're going to need your calculator next to you right now. If you put that in your calculator, you'll do second square root 4, the second button, plus 3, the second button, and you'll get 5. So that's what you should have gotten. So that's the first part of our answer. First part of our answer is 5 kilometers per hour. But we're not done. Now we're going to have to do 3. We have to find our angle. Okay, so we're finding the angle of the triangle. That's not finding the position yet. So we're finding our angle. So to find our angle of interest, it's this right here. This is our angle of interest. And we want to make sure that we use the sides that are already given to us, which was 4 and 3, just in case we messed up on the 5 kilometers per hour. So I'm going to use, well, let's first make sure we have to identify our sides. So we know our hypotenuse is 5 kilometers per hour, and our angle of interest is right here. So we can name the side. This side, because it's next to the angle, is the adjacent side. So because this is the right angle, this is opposite. So what formula or trig formula would I use that has opposite and adjacent relationship? So think of SOHCAHTOA. So TOA, T-O-A. So if I find my angle, I've got to get the inverse of tangent, and I'm going to take my opposite over my adjacent. So when I plug this into, so you now on this you now on the A and B on here, it didn't matter who was where, 4 or 3, it doesn't matter, but on this it does. So you have to have your 3 up here, and you have to have your 4 down here, and you put that in your calculator. And by now we should know how to use this. Second tan, and that gives you tan inverse. Make sure that your calculator is in degree, and then you're going to put in 3 divided by 4, and you should have gotten 30. I have 37. Okay, so I got 37 degrees. Well, it was 36.5. No, it was 36.8698297, and I would like 2 numbers, so please give me a 37 degrees. Okay, so we're not done. This is 37 degrees right here. Okay, 37 degrees. All right, now my x component is here. This is where my x component is right here. So I'm going to go from my x component and draw towards my hypothesis. And I know that I'm starting at 0 and I'm going away from my 0. And my instructions say when I'm going away, I do what? I add. And so our little cheated notes say that if I'm going away, my angle is going to be added to 0. So 37 is my actual location. And you can actually say 37 degrees, you can call it northeast, okay? Because it's like right in the middle of north and east. And it would be 5 kilometers per hour, 37 degrees northeast. So that would actually be your actual answer there. Because if we're going to truly do what the definition of velocity is, and that is including the including the location or the direction, we've got a 37 degree northeast right there. Okay, this is fun stuff, good times. So we are going to be doing this for the next 4 and 5, example 4 and 5. Good practice, good stuff. So let's do example 4. Example 4, we got the Matten family, they're going on a trip. And so we have 700 kilometers west. So I'm going 700 kilometers this way. That's west. I'm going to label it because all that stuff was crazy. Now we're doing the same thing that we did earlier with a twist. So we don't have something going against us. We're just going direction. So the family is actually walking 700 kilometers west, or they're driving, not walking. And then they drive 600 kilometers south. So let's try to make this look like 600 the best we can without looking like 700. I think that's shorter. Okay. It's not very nice and straight, but you can do that on your paper. So that's 600 kilometers. Let me get my 600 here. Maybe I can straighten that up. It's going to bother me. Okay. And then the family is going 400, nope, 300 kilometers east. So I'm going to say if this is 700, that's kind of about half. So I'm going to go about just less than half. Let me straighten that puppy up. Okay, I'm going to go there. This is 300 kilometers. And then I'm going to go 400 kilometers north. I want to go 400 kilometers north. So 400 is a little bit over 300, and 300 is about half of 600. This is 400 kilometers. Now, because it's asking me where will the family end up in relation to their starting point, I want to know where they are. That means I had to find a direction. So this is not just calculating the displacement, guys, and just getting that one resultant. We've actually got to go through all the rigmarole of putting at our starting position, putting the compass, doing the angle thing, and all of that, the all 6-step stuff, okay? So where is my starting position? The starting position was right here. Now remember, I always draw my resultant from the starting position to the ending position. So this right here is my resultant, also my hypotenuse. Right here is where I will draw my little compass that's going to help me decide whether I add or subtract depending on what quadrant that I'm in, okay? Okay, so I'm going to use red because I've got to find a triangle in this. And so look at your picture and see where it makes most sense to have your triangle. And that is going to be right here, right there. So now I have to find my two sides, okay? Now I can find my resultant by the Pythagorean theorem. So hypotenuse, I can find that no problem in a minute. I know how to do that. But finding my A and my B is very, very easy. It's very simple math. So I know that this total blue distance right here, or top line, is 700 kilometers. And the one on the bottom, the red one that says 300 kilometers, I know that that stops right here. So the difference between 700 and 300 is 400. So this right here, I'm sorry, let me get my 400. I was going to write in red. That's why I said I'm sorry. That's 400 kilometers right there. So my x component is 400 kilometers. This is my x component right here. So now I got to find my y component. My y component is this little section in the dotted red. Now I know that my green over here, 600, my 600 kilometers is the distance from here to here. And my little dotted area is within that 600 kilometers. I know that right here is my 400. So the difference between these two distances, 600 and 400, is 200. So this is 200 kilometers. All right, now I've got my sides. I have my A and I have my B. I can do the Pythagorean theorem. So let's take my checklist. Let's make sure we've got our checklist handled. One, we did a picture. Okay. Two, now we're going to find our sides using the Pythagorean theorem. Or no, not find sides. We're going to find the hypotenuse using the Pythagorean theorem. So c squared equals b squared plus a squared. I could have written that a squared plus b squared. Okay, I'm going to shorten this up. So it's going to be 200 kilometers squared plus 400 kilometers squared. Okay, so my hypotenuse is 447 kilometers. Okay, that's my hypotenuse. Now, I'm not done. That's just part of my answer. Okay, that's my kilometers. Now I've got to find, okay, where at? Where in the world is this? So notice I've already drawn, I think I've already done step, well, I've done half of a step. So step 3, I now have to find my angle. Angle of what? What angle? Well, your angle of interest. Well, what's my angle of interest? Your angle of interest is this right here. It's right inside of where you started. So the point at which you start, your starting point, so where the tail of your resultant is, that meets the tail of your x component, which is where you started, that is always your angle of interest. And that's how you're going to be able to identify your sides. So now I'm going to do step 3. And I got to figure out what formula I'm going to have to use. Now, granted, I could use any of them because I have all 3 sides, but I know without a shadow of a doubt that 200 and 400 are right. So if this is my angle of interest, and I know that this is my hypotenuse because my resultant is usually my hypotenuse, okay, my x component is then identified as my adjacent because it's next to this angle right here. Therefore, my 200 is my opposite. So it is important on this particular step that we do not get O and A confused. Okay, so let's go ahead and put that into number 3. So what formula has a relationship between O and A? It is tangent. Remember SOHCAHTOA? SOHCAHTOA. You might want to write that down if you're not real strong with this. Oh, I said it. I wrote it wrong. Oopsie. That should be an A, not an O right there. Okay, so A. Okay, so I want my angle. So I'm going to get the inverse of tan. My O is 200 kilometers. My A is 400 kilometers. Put that into your calculator. And so I got 26.5650511, and that would be a 27. So my angle right here is 27 degrees. That is the actual angle from my x component to my hypotenuse, but that is not where I'm at because 27 degrees, guys, is actually over here. Okay, so now I have to do step 4. Okay, step 4, we call that, let's find the direction. So we're going to find the direction. And that's where I have to use my compass. So I always draw my compass where I began my journey, okay, or where the object began its journey. That's where you draw the compass, okay. So let's get busy doing that. Notice here's my 0 degrees. That's also my x component. Now my x component is all the way over here. So I am drawing from my x component to my hypotenuse. So this is away from 0 degrees. So it is away from 0 degrees. So that means if it's away, I'm adding. Okay, but look at what quadrant that I'm in. So looking at that quadrant, and so in that particular instance, we are going to add the angle to 180. So the rule says if I'm moving away from degree 0, how do you know, Ms. Klein, what is your reference point? My reference point is my x component. My x component is telling me which way I'm going. So I draw my arrow starting at my x component going towards my hypotenuse, always, okay? My x component towards my hypotenuse. So that means 180 degrees plus my angle, which is 27 degrees. So you end up getting 207 degrees. So your total answer is 447 kilometers at 207 degrees southwest. If you want to add the southwest, you don't have to because we know that 207 degrees is in the southwest quadrant of our compass. So that's how we do example 4. So let's go to example 5. Example 5, we have the St. Louis Cardinals home run king, Mark McGwire. He hits a baseball due west with a speed of 60 meters per second, and the ball encounters a wind that blew it north at 10 meters per second. What is the resultant velocity of the ball? And on example 5, because of velocity, yes, we're going to find the location. We're going to find the direction, okay? So let's do it. So we have a pretty interesting situation here where the ball is going west 60. So this is 60 meters per second. And the wind is encountering the ball and it blows it this way north 10 meters per second. All right, so my resultant, or now my hypotenuse, is that. So this is where I started right here, the red dot. So I'm going to draw my compass right here. I'm just going to go ahead and get that started just because that makes me happy, but you don't have to do that. So number 1, draw. Okay. Number 2. Number 2. Well, we got our triangle. We find our triangle. So you find the triangle. We did that. I just didn't write that as a step earlier. So number 3, what do I want to do? I want to find my resultant or my hypotenuse. Okay, so I'm going to use this. So that's easy. So I'm going to go down here. I'm going to find C. Remember, I'm just going to square root. I've got 60 plus 10 squared. So I do all of that. Put it in my square root. So I go in my calculator. Second, square root, 60 squared plus 10 squared. Doesn't matter who I put first, 60 or 10. I get 61 meters per second. Okay, so now this client, it said velocity, and I know in class I said we won't worry about direction, but we're going to do direction because we need to practice it, okay? So, and it does say do direction, so we're going to do that. So let's see here. What do we start with? Let's go to step number 4. I don't know if you can see this on the black, but I'm running out of room. Step number 4 is, oh, got to find my angle. So where's my angle? My angle is right here. It's my angle of interest. How did you know that, Miss Klein? Because that's where I began. That was my starting point. That's how I know that. So I have to find my angle inside of the triangle, okay? So to find the angle inside of the triangle, step 4, I have to use my trig. So that means I got to identify my sides. So this is my hypotenuse. If this is my angle of interest, that makes this the adjacent and this over here the opposite. Okay, so I can see that I've already been given this one and this one, so I want to use the formula that has A and O as a relationship, which is the inverse of tangent, opposite over adjacent. So opposite is 10 divided by 60. Put that in your calculator. So we're going to go second, tan 10 divided by 60 equals, ooh, you should have gotten 9 degrees. My calculator says 9.462322208. So I'm saying 9 degrees. Okay, so step 5. We found the angle. The angle right here is 9 degrees. Now look, you know that's not 9 degrees because 9 degrees would be way over here, literally, actually. But it's not. It's over here in the second quadrant. So now we have to find our direction. Find our direction. So remember, I go from my x axis or my x component, which is also the horizontal. So this is 9 degrees to the horizontal. That's another way of saying this angle right here, 9 degrees to the horizontal. I'm going to go this way. Oh, looky there. We are going towards this, which is 0 degrees. Okay. Now I got to go and look at my little rules that we talked about earlier. And if that quadrant, if I'm going toward 0 degrees, I'm going to subtract 180. I'm going to subtract my angle from 180. So, I'm finding my direction. Here is 180 degrees. I subtract my angle, and you should have gotten 171 degrees. So your final answer is 61 miles per second, 171 degrees. You would say northwest if you wanted to add that there. So that's how you do number 5. And then one more, number 6. Now this was confusing for everybody because we threw the word north in. Don't let that, it's just a number. Don't let that throw you out of the way. And also because our notes didn't use the language of components and to the horizontal and blah, 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 it gets confusing. But in this lesson, I've been using that, so hopefully it'll set you up for success on example 6. Ralph is mowing the backyard, and he is pushing the mower downward with a force of 20 degrees north at an angle of 30 to the horizontal. So this is telling us how to draw this. So here we have Ralph, and he's got his little lawnmower. Here's his handle. Oh, that lawnmower is way bigger than him, isn't it? That's okay. There's his lawnmower. And he needs to be taller. Okay. Now you can draw this picture. You don't have to draw a picture like that. Okay, there, he's a lot bigger. Okay, that looks better. He's happy. And so it says to the horizontal. Well, it says right here, he's putting a force of 20 newtons at an angle. So if this is the horizontal, that's my x axis, okay, here, where the lawnmower is right here, this is my 30 degrees right there, which would mean this is my hypotenuse, and this is where the 20 newtons go. So over there is my y component. All right. Okay. So, since that is the angle, this is going to be right here. My angle right here is going to be where I'm going to draw my compass. Okay? So, I would encourage you on this particular picture to take that out and put it here. Okay, it gave us this resultant already. And it told us that it was to the horizontal. And that this is a 30 degrees to the horizontal, which sets us up to do this as our compass. All right? And so we know that this is 20 degrees. So we are going to have to do things a little bit differently here. We want to know what the horizontal and the vertical components of the force exerted by Ralph are. It's not asking us to find the direction on here. Yay! Okay, but I just did that because I'm just thinking that way. But yay, we only had to find our x and our y component. So here's our x component, and here's our y component up here. So this time, no direction, just what are the horizontal and the vertical components. Now remember, horizontal is going from side to side, and that always represents y, and vertical is up and down. I'm sorry, horizontal goes from side to side, and that always represents x, and vertical is up and down, which represents y. So I've got to find basically a and b, but I don't have two sides. I've only got one side. So let's identify. So we can use trig. So if this is my angle right here, and I know this is my hypotenuse, this would be my adjacent. Therefore, this is opposite. So I have now identified. And so I have H, and well, you just decide which one you want to use, O or A. So remember, let me erase this fella. So remember this, SOHCAHTOA. All right. So let's see. I'm going to go ahead and find A first because it's the first letter of the alphabet. So which of my formulas is going to have A and H in common? So it's cosine. So I want cosine of the angle, A over H. I need to find A, so I'm going to get H out of the way. So A is going to be 20 newtons times cosine of 30 degrees. 20 cosine 30 is 17.3205. I'm asking you to write 17. So A equals 17 newtons. So 17 newtons. And so now I have found that. And now I can find the other one. So because I want to stick with 20 and 30 because those were numbers that were given to me, and maybe I did it wrong for 17. Maybe I got that one wrong. I'm going to use the formula that has H and O relationship. So sine of the angle equals opposite divided by hypotenuse. And I get my h out of the way. So I'm going to take 20 newtons and get the sine of the angle 30 degrees. So I put that in my calculator. And you should have gotten 10 newtons. So here is the answer, 10 newtons. And you can show me the answer by labeling your picture, or you can show me your answer by saying this. A equals 17 newtons, O equals 10 newtons. Either one is acceptable. And that is the end of our vector lesson. Thank you for joining me.